So this video is the continuation of the previous one, and so it will be still on factor groups, but this time we are going to see a very important theorem. The quotient group of the factor group of G by the center. The factor group of G by the center theorem. Let G be a group and ZG the center of the group G. If the factor group of G by the center is cyclic, then G is abelian. Okay, so I prefer to call this or I like to call it the quotient group of G by the center. Okay, quotient group or factor group is the same. So okay, if G is a group and ZG is the center of G, the quotient group of G by the center, if the quotient group of G by the center is cyclic, then G is abelian. And we are going to do the proof now. Okay, let G, so center of G, G center of G be this G stands for generator. So let this be the generator of the quotient group or the factor group. Okay, so this one is a generator of the factor group, and we will pick A and B in G. Okay, so there should exist integers I in J such that A left coset of the center will be equal to generator here I times. Okay, so that will be G to the power of I left coset of the center. Okay, and same for the element B, so there will be a B left coset of the center equal, so generator of the center, that one was to the power of I, this one will be to the power of J, where IJ center of G. Okay, do not forget that by hypothesis the quotient group or the factor group is cyclic. Okay, so since it is cyclic, there will be a generator, right? And so we call this one the generator. Okay, so the left coset of the center will be equal to the generator, right? Or at least to a power of the generator. Okay, and for another element the same here. Okay, but this being true, so A, do not forget A is in G, an element in G, will be equal to the generator power I of X, and this X will be in the center. Okay, and there will be a B, G to the power of J x. X, no, we have to call it something else, right? Y. Let us say y. For y in the center, right? Okay, so this is A, some power of the generator, times x an element of the center, and B will be some power of generator, another power, another element in the center. Okay, question, what is AB? So AB will be GIX times G power of J Y, right? Okay, this is due to this, right? They are all elements in a group, okay? So we can say GI X, I can associate them this way, right? Okay, but here X times generator can be generator times X, right? So I can do GI GJ XY, right? And I can associate these two. Okay, now, so GI GJ XY and GI GJ YX, right? Now I can associate them again in different order, so I will get, wait, I have to change here, so this is GI GJ XY, so I change those two and I change those two, right? So this one will be J, this one will be I, right? And I can associate these two. And now I can do DJ Y GI X, right? So there will be equal to BA. Okay, so AB equals BA. So the factor group of G by the center is AB equals BA, a billion. Okay, and this concludes the proof. This theorem is very good to prove some other things, like if we close follow the previous proof, we see that we get much better results, like if the factor group G by H is cyclic, and if H is a subgroup of the center of G, then G is a billion. Okay, many things can follow from this fact, okay, and from this theorem. Also, what is used a lot is so our theorem says if the quotient group of G by the center is cyclic, then G is a billion. Okay, But the contrapositive is also a very important theorem. Meaning, if we say if G is a billion, if G is non-abelian, so this is the contrapositive. If G is non-abelian, then the center is not cyclic. Okay? So, following this, if we look back at the Lagrange Theorem, if you have a group, let us say G, and let us say the order of this group G, let us say that G is non-abelian. Okay, if G is non-abelian, so if G is non-abelian and it has order PQ, where those two are prime numbers, okay, so the center is not cyclic. So the center of G should be trivial. Okay, and this is very important. Okay, this is the contrapositive of our theorem. Okay, now we go into another very important theorem, the isomorphism between the quotient group of G by the center and the inner automorphism of G. So, for any group G, the factor group of G by the center is isomorphic to the inner automorphism of G. I'm going to take the proof quickly. Okay. So consider the correspondence between the factor group of G by the center and say the inner automorphism of G, and this one will be given by T. I'm going to write it center of G and G, the center, phi of G. Okay, so do not forget that this phi is phi G of X is inverse, left inverse xg, okay, for all x in G. Okay, first we have to prove that this T is a function. Okay, suppose the center suppose that the center of G equals the center of H. Okay, so if this is true, H times the inverse will be in the center, right? Okay, if that happens, so for all x in G, x will be equal to H times G1 inverse, right, times X H G1 inverse. So that will be G H inverse X H G inverse. So this will be G inverse XG equals inverse H inverse XH, okay, for all x in G. So this means that phi of G equals phi of H. Okay, if we reverse the argument, we show that T you easily show that T is 1 to 1, okay, and it's also obvious that T is onto. Okay, let us check if T is operation preserving. Well, I think that follows directly from the fact that phi of G, phi of H equals phi of GH, right, for all G and H in G. And that concludes the proof. I did very quickly. If anybody has any problem, just ask me. We just saw these two very important theorems, right? And we are going to use them now. We saw that if the factor group of G by the center is cyclic, that means that G is abelian. And we just saw that the factor group of G by the center is isomorphic to the inner automorphism of G. Now, let me give you an example how to use these two very important theorems, or an application for those two theorems. Imagine you want to find the inner automorphism of the dihedral group 6. Okay, we are going to do this without looking at the inner automorphism. So, easy to check that the center of D6, the order of the center of D6 is 2. So, the order of D6 by the center of D6 will be obviously 6, right? The order of D6 is 12, right? The order of the center is 2, so 12 dividing 2, the order is 6. So now you can go back and look at our classification of groups of order 6. We're going to look for groups, we're going to look for groups of order 6. And we know that the inner automorphism of D6 is isomorphic to D3 or to Z6. Okay, now if the inner automorphism of D6, if this one is cyclic, then using this since they are isomorphic, so since the inner automorphism of D6 should be isomorphic to the factor group of D6 by the center. Okay, so this one should also be cyclic, right? So I'm going to repeat it. If the inner automorphisms D6 were cyclic, since it is isomorphic to D6 factor group by the center, so this one should be cyclic too, right? Yes, so D6 by the center should be cyclic too. But if this one is cyclic, then by this very important theorem, if D6 by the center is cyclic, it would imply that D6 is abelian. Okay, so we conclude that the inner automorphism of D6 is isomorphic, obviously, to D3. See?